In this video, I'm going to show you a setup for simulating resistive circuits where the resistors can be varied in a Gaussian fashion for Monte Carlo simulations. And this will be foundational for a DAC tutorial that I'm going to do subsequent to this. So the setup for Monte Carlo simulation is going to be very similar to the one that I went through for the Skywater 130 technology in the NMOS 01V8 and the PMOS or PFET 01V8 and the NFET 01V8. So it's the same style of setup. So I have here under Documents and MC V divider toot. I have a couple of symbols and a schematic. So let me open up the symbols first so you can see what I've got going here. So Xschem Gauss res.sim, and I basically just copied the class resistor symbol from the library and have made a couple of small changes to it. I deleted the M parameter and I changed the type from resistor to primitive, and I've changed the template so that instead of being R1 it's XR1. So this is going to be written out when we netlist from Xschem, or we generate a Spice netlist. We're going to get a subcircuit reference, and then we'll have another symbol which contains the subcircuit definition, which has a resistor in it with the Gaussian variation. And we're going to have the ability to turn that on and off with a parameter called MC switch, just like we have set up for the Skywater 130 technology with the FETs. Okay, so we have here also at name, so XR1, XR2, XR3 is going to be what gets written out first in the format here. The pin list, which is basically going to be positive and neg for the two pins on the thing. The symbol name, which is the subcircuit name, which is going to be Gauss res, and then this parameter here, nom, is the nominal resistor value, and that's what gets filled in here when we put a value in here. So the nominal or the default value is 1K. So now I'm going to open up this other Gauss res def, and this is sort of like the TT models block. I just copied the code symbol and has specialized it. And so here's what's inside the global property. Here we have the definition of a parameter, which is called MC underscore switch, which is set by default to 0. And so that will by default mean that these Gauss resistors do not have any variation. And each of these is defined to be a subcircuit. So the subcircuit is called Gauss res to match the name of the symbol. And then the two terminals pos and neg. We have some subcircuit parameters, including the nominal 1K, which is the default value here, that gets passed in the subcircuit instance definition. And then we have this parameter called CV, which is the coefficient of variation. Okay, that's the standard deviation divided by the mean. And here is the element, the one element inside of our subcircuit, which is just a resistor that goes from pos to neg. And the value of the resistor is the nominal value plus MC switch, which we're going to be 0 or 1. 0 turns off the variation, 1 turns it on, times an absolute Gaussian pseudo-random variable with 0 mean, unit standard deviation, and then we're multiplying that by CV and then by the nominal resistance again. So this gives us a Gaussian variation about the nominal value with some like 0.5% if we take the default CV here. And then dot end as for end the subcircuit. Okay, so that's the setup. And now I'm going to open up our voltage divider circuit. And this is basically just two of these Gauss resistors. Notice they're XR1 and XR2, and they have values of 1K each. I've got an input voltage source, so it's just a two-way voltage divider with a divider ratio of 1/2. And here's the Gauss res def block, and I've set the Monte Carlo switch here to 1, so we're going to get variation. And the control block basically is set up as follows. We're going to turn on the vector names at the top of the text file we're going to write out. We're going to set the scale, which is the voltage that's being swept, only to appear once instead of once per other vector that we save. We're going to do 10 runs, so we're going to let runs be 10, let run equal 1, that's our running index of the run number that we're on, and we have a while loop here. While run is less than or equal to runs, we're going to do a DC sweep from 0 to 1 in 10 millivolt increments. And then we're going to write the data to a file in the directory that our schematic is in, and the text file is going to be called MC vdivider, and then we're going to insert the run number into the name of the file, .txt, and we're going to write just the output voltage vector. We're going to reset. That's going to regenerate the Gaussian random variables. It's going to pick new ones for each of the resistors. We're going to bump the run number up by 1 and then go back around the loop. And that's it. So if we netlist and then, apparently we need to set the netlist options. So Xspice netlist, let's save that. Netlist simulate, and it's actually done. And if we go set plot, we can see there are, yes, 10 runs here. And we could, if we wanted to, plot dc1.v of v out, dc2.v of v out, dc3.v of v out, dc4.v of v out, just to see what that looks like. And look, there are, so this is going from 0 to 1 volt, and we'd expect a divider ratio to be 0 to 0.5 volt, and we get that, but we do have some spread here in our voltage divider voltage transfer characteristic here. So let's quit this and let's flip over to a terminal. So we'll pull up another terminal window, and we'll go into Documents, MCV divider, toot. There are 10 text files. We can use this Python environment that I have set up. And if we do, let's see, say vout equals empty list for I in range 1, 11, load Ngspice format MCV divider I.txt, and we're going to do vout underscore append, and I think it's going to be capital vout and vout is indeed a list of 10 numpy arrays. We're going to say vn equals v underscore sweep, and we can do plot vn comma vout underscore, and there are our voltage transfer curves plotted, and we can make it big. We can kind of zoom in up here and see that we do have some spread here. And so if we wanted to, we could write a little Python loop that basically goes through and fits a straight line and sees what the divider ratio is We could look at the distribution of the divider ratio, for instance, if we wanted to. That's Monte Carlo simulation with sort of Gaussian variation of resistors. Interesting in its own right, but it's a stepping stone to a resistive ladder DAC tutorial, which we'll put out in a little while. Thanks for watching.